Welcome to the deep dive. If you've ever felt that intense pressure to deliver software faster and faster, but you're also wrestling with that critical need to keep it absolutely secure, then this deep dive is definitely for you.
Yeah.
We are plunging headfirst into that really complex, sometimes kind of chaotic intersection where rapid IT delivery, the engine powered by things like DevOps, meets the stark and unforgiving reality of modern cyber threats.
Absolutely.
We've gathered insights that really unpack the profound challenges organizations are grappling with right now. We're looking specifically at how these sophisticated attackers are targeting the very tools built for speed and agility. And maybe most importantly, revealing concrete strategies and practices that can actually make a real difference in defending against them.
That's right. And today isn't just about understanding the problem, right? It's really about exploring the necessary evolution of security itself.
Yeah.
We're going to see why security just can't be an afterthought, a check at the end of the line. It absolutely must be woven into the very fabric of software development.
From the very beginning.
From the moment an idea is conceived, yeah.
Mm-hmm.
Through every step of writing, testing, deploying code, it's really about gaining a deep understanding of the modern battlefield shit. The tools, the automated pipelines, the dynamic cloud environments.
Right.
And equipping ourselves with the knowledge of strategies and technologies that offer robust real-world protection.
So our mission in this deep dive is, I think, clear and pretty critical. We need to unpack the technical and, the cultural complexities in securing these really fast-paced IT environments. We need to highlight the precise ways attackers are exploiting common misconfigurations and, those subtle vulnerabilities within these systems.
Yeah, the ones people miss.
Exactly, and reveal the specific strategies, the tools, and crucially, the fundamental practices that can create a tangible layer of defense for your vital digital infrastructure. I mean, this is a topic with incredibly high stakes.
Oh, definitely.
Think about this. Finding and fixing a security bug late in the development process, say during final testing or even after deployment, it can cost anywhere from 6 to a staggering 15 times more than if you'd caught it back during the initial design or coding phase.
That cost isn't just theoretical either.
No, it's hard dollars, it's wasted time, and maybe worst of all, it's leaving your organization wide open to potential compromise.
And the attackers. They are acutely aware of this. They understand the pressure points. They know the common mistakes made in that rush to deploy and the vulnerabilities that pop up when security isn't integrated properly from the start. We'll be looking at some real-world attack campaigns that are actively exploiting these weaknesses right now, specifically targeting the tools that enable that rapid deployment.
Okay, but before we fully immerse ourselves in this, this deep dive is brought to you by Stonefly. They're a leader in enterprise storage, backup, and disaster recovery, AI storage, and cloud solutions. So, if you're looking for secure, ransomware-proof storage solutions that offer genuine protection for your critical data, Stonefly really specializes in air-gapped and immutable storage.
That's crucial stuff these days.
Absolutely. To learn more and schedule a demo, just contact sales at stonefly.com. They can really provide that bedrock of security for your data in this fast-moving world.
Good to know. Okay, so let's start by really unpacking this fundamental collision we see happening across organizations today. This intense market-driven demand for speed, powered by the widespread adoption of DevOps practices.
Yeah.
Clashing head-on with the absolutely non-negotiable requirement for robust security.
It's really a defining characteristic of modern IT, isn't it? Organizations are embracing DevOps not just because it's trendy, but because it's, essential.
Right.
It's essential for building and shipping software at the velocity customers expect and the market demands. Whether you're an online retailer, a bank, a software company, speed to market with new features, bug fixes, it's a competitive differentiator.
No question. The challenge, though, is that traditional security approaches, often built around slower, more deliberate processes, define perimeters. They just haven't kept pace with this rapid evolution.
It often feels like security is perceived as the brake pedal, right? The thing that slows down that agile, rapid development cycle that DevOps enables.
Precisely. And when that perception exists and the pressure for speed is just paramount, security activities often get, deprioritized or delayed.
Pushed to the side.
Exactly. And this leads to the accumulation of what we call security debt. You're pushing code through quickly, maybe skipping rigorous security testing, maybe delaying vulnerability patching, or overlooking minor misconfigurations just to hit a deadline. Each of those skipped steps or delayed fixes adds to a backlog of vulnerabilities and risks. You're essentially borrowing time from security today.
at the cost of much greater risk tomorrow.
Exactly. Prioritizing speed at the explicit cost of security creates an environment that is inherently vulnerable and, in the long run, far less productive and way more costly than building security in from the start. Striking that balance between velocity and resilience, that's the core challenge.
So how do we even begin to tackle that balance? This is where the concept of DevSecOps comes into the picture. And we hear this term shift left constantly. What does shifting left actually mean in practice, and why is it so crucial?
Well, traditionally, security was largely confined to the later stages of the software development lifecycle, the SDLC.
Right.
Think of it like a gate at the very end. Development teams would build the application, write the code, and then, maybe in staging or pre-production, the security team would step in to test it for vulnerabilities.
It's like building an entire skyscraper and then bringing in the structural engineers to see if the foundation is sound.
Exactly. That's a great analogy. And, predictably, when you find significant problems at that late stage, structural flaws, architectural weaknesses, deeply embedded vulnerabilities, they are exponentially more expensive and time-consuming to fix.
That statistic you mentioned.
Yeah, the IBM research one. Fixing a bug found during implementation costs about 6 times more than finding it during design. And fixing it during testing or post-release, that can cost up to 15 times more than finding it back in design.
And why is that? What makes it so much harder later on?
Well, think about it. A bug found in the design phase is just, a drawing on a whiteboard or line in a document, easy to erase or change.
Right.
A bug found during coding might be a few lines of code to edit, but a bug found way down the line in testing. It's baked deep into potentially complex code, it's integrated with various services, deployed across multiple environments.
Oof. Unwinding all that sounds like
It requires significant rework, tons of retesting, coordination, redeployment cycles across dev, ops, security. It's a massive drain.
So DevSecOps and this shift left philosophy it embodies, it's fundamentally about moving security activities, responsibilities, considerations much earlier into that SDLC.
Precisely. DevSecOps means integrating security testing, automated controls, and a security-first mindset across the entire SDLC. It starts right at the initial idea phase, continues through design, architecture, coding, testing, deployment, and even into ongoing monitoring and feedback. Shift left is the practical application of this. It means empowering developers, ops engineers, QA testers, product managers to think about security from the outset and, crucially, to remediate issues as early as possible in their own workflow.
So the goal isn't necessarily to turn every developer into a security guru,
No, not at all.
but to give them the tools and knowledge to handle common issues themselves early on.
Absolutely. It's about distributing security responsibilities and embedding automated checks into the tools and workflows that teams already use day to day. You want developers fixing security vulnerabilities in their code while they're still writing it or as part of their standard code review.
Not weeks later when they've already moved on to something else.
Exactly. Instead of having a security report land on their desk weeks later about code they barely remember writing. This early detection and remediation capability is where the massive cost savings come from and why it's so effective.
It seems almost, well, intuitively obvious that catching issues early is better. What are the tangible benefits organizations actually see when they successfully implement DevSecOps?
Oh, beyond the cost savings, the benefits are numerous and really significant. Your code becomes inherently more secure over time because security isn't just a single gate, it's a continuous process, integrated into every step.
So a stronger security posture overall.
Definitely. You reduce overall business risk by proactively identifying and mitigating vulnerabilities that attackers could exploit. It significantly improves your compliance posture too, because security requirements and checks are built into automated workflows, making audits and reporting much easier.
And collaboration, does it help with that?
Crucially, yes. It fosters improved collaboration and productivity across those traditionally siloed teams, dev, security, ops. They start working together towards a shared goal, building secure software rapidly, rather than security being seen as this obstacle or bottleneck. Honestly, in the modern threat landscape, DevSecOps isn't just a nice-to-have anymore. It's rapidly becoming a fundamental necessity for organizations to operate at speed while managing risk effectively.
Okay, so if DevSecOps is about integrating security throughout the SDLC, the engine powering that high-speed process is typically the CI/CD pipeline, continuous integration, and continuous delivery. How does securing that specific pipeline become the foundation for DevSecOps success?
You've hit on a really critical point there. The CI/CD pipeline is that automated workflow that takes code from a developer's laptop, builds it, tests it, and deploys it out to production.
Right, the assembly line.
Exactly. And if this pipeline itself is insecure, if vulnerabilities get introduced during the build, if sensitive data is exposed within the pipeline, or if the tools themselves are compromised, then the integrity and security of every single application deployed through it are at risk.
Wow, okay.
Security issues in the CI/CD pipeline directly impact your final application security and, frankly, open the door wide open to sophisticated cyber risks, as we'll see with those real-world examples later. So securing the pipeline is the absolute bedrock upon which effective DevSecOps is built. You can't skip it.
So what are the concrete practices then? What should organizations be implementing to build a truly secure CI/CD pipeline?
Well, it starts with pushing security considerations as far left as possible, right within that workflow. You need mechanisms to identify and address security bugs early, within the development and integration phases of the pipeline itself.
So automated checks kicking off as soon as code is committed.
Exactly. But even earlier than that, you should be defining security objectives and requirements before coding even begins. Make them part of the initial design process.
Threat modeling, too.
Absolutely. Incorporate threat modeling during system conceptualization. Actively think like an attacker. Where are the potential weaknesses in this design before we write a line of code?
Getting ahead of the problem. Smart.
It's crucial. Then, you embed automated tools throughout the pipeline. Leverage linters and static analysis tools right at the initial code check-in stage. These automatically catch simple coding issues, enforce secure coding standards, maintain code quality.
Basic hygiene checks.
Exactly. Then, use software composition analysis, SCA tools. These automatically check all your open source dependencies for known vulnerabilities. Given how much modern software relies on third-party libraries, this is completely non-negotiable.
So identifying risks in the components you're pulling in from outside.
Yes. Next, integrate static application security testing SaaS tools directly into the automated build pipeline. These scan your own proprietary code for more complex security vulnerabilities, logic flaws, and often perform another layer of SCA as well. After the build is complete, conduct automated security integration tests to verify that different components and services interact securely. And importantly, security testing absolutely cannot stop after deployment.
Right, you need to test the running application too.
You have to run dynamic application security testing, DAS scans, and conduct penetration testing post-production to find vulnerabilities in the running application in its live environment.
And patching, configuration.
Automate it. Automate patching and configuration management within the pipeline to ensure that all dependencies, libraries, and the infrastructure itself are kept up to date with the latest security patches and configured securely according to your policies.
It really sounds like automation isn't just for speed here. It's actually fundamental to enabling security checks at the speed and scale required by DevOps.
It absolutely is. Automation allows you to implement a vast number of security checks consistently, repeatedly, and rapidly throughout the development and deployment cycle. This ensures that security measures don't become that manual bottleneck that slows down crucial fast delivery. It makes security part of the speed, not an impediment to it.
Okay, so the principles make a lot of sense, and securing the pipeline is clearly key. But actually doing it, implementing DevSecOps across an organization, must come with significant real-world challenges. The material identifies 7 critical ones that organizations commonly face. Let's maybe dig into each of those, starting with what seems like a foundational issue. Simply building security into the pipeline itself. It sounds technical, but is it more than just plugging in tools?
Oh, much more. Embedding security effectively isn't just a technical challenge of integrating tools. It's fundamentally a cultural one.
The people problem.
Yeah, exactly. We touched on that traditional siloed environment where dev focused on speed and features, ops on stability, and security on risk reduction, often acting as that final gatekeeper, right? That structure inherently creates friction. It clashes with the collaborative high-speed goals of DevOps. Getting these teams to truly work together, to understand and respect each other's objectives, pressures, day-to-day realities, that's difficult. It takes real effort.
So it's about breaking down those organizational walls and fostering a sense of shared responsibility for security.
Exactly. It requires seamless, ongoing communication and a shared understanding of the goals. Leaders really need to champion this cultural shift, ensuring teams share information freely and understand how their activities impact others.
Like developers understanding why a security requirement exists.
And security teams understanding the practical constraints and pressures developers face.
Exactly. This is another area where security automation really helps address that cultural resistance.
So,
Well, by minimizing the manual effort for security tasks and drastically reducing the time it takes to get feedback on security posture, think automated code analysis versus waiting weeks for a manual review, you help bridge that speed gap.
I see. Developers get quick, actionable feedback, making security remediation less of a disruption and more just a natural part of their workflow. It feels less like an external imposition.
That makes perfect sense. If the security feedback is fast and integrated, it doesn't feel like some separate bureaucratic process slowing things down.
Right. Okay, moving on to the second challenge. Taming your exposed attack surface. With the massive and rapid adoption of cloud environments, this attack surface has expanded dramatically compared to, the relatively contained perimeters of traditional on-prem data centers.
Because in the cloud, the boundary isn't just a firewall at the edge, right? Resources are distributed and accessed differently.
Precisely. The concept of a hard-defined network perimeter kind of dissolves in the cloud. And the danger here is how easily misconfigurations or even seemingly small manual errors can inadvertently expose critical resources publicly to the internet.
Yeah, you hear about leaky S3 buckets and things like that all the time.
Exactly. Traditional perimeter-based security just isn't sufficient to protect these dynamic, software-defined environments.
So how do you manage that much wider, less defined potential entry point for attackers then?
Well, automated security checks integrated throughout the SDLC become absolutely essential. Tools like SAST, DAST, SCA, and IAST, which we discussed for the pipeline, are also critical here. They find vulnerabilities before they get deployed to environments with potentially wide exposure, minimizing the attack surface right from the start.
Okay.
But beyond vulnerability scanning, you really need to think about securing the infrastructure itself. This is where concepts like security as code, testing as code, and compliance as code become vital.
Can you elaborate on security as code? What does that actually look like?
Sure. Security as code means defining your security policies, configurations, and controls, not through, say, manual clicks in a cloud console, but as actual code. Use configuration management tools like Terraform or Ansible, or policy as code frameworks like Open Policy Agent, or even just scripting. This code, defining things like network segmentation rules, identity and access management policies, required server hardening settings get stored in version control alongside your application and infrastructure code. It's reviewed, tested, and deployed automatically.
So it's treated just like application code.
Exactly. This ensures your security configurations are consistent, repeatable, scalable, and much less prone to human error compared to manual processes. Testing as code extends this to automate the security testing itself, and compliance as code builds automated checks and reporting into your pipelines to continuously verify adherence to regulatory requirements.
So it ensures security isn't just a manual add-on, but it's built into the very foundation of your cloud environment in a consistent and scalable way.
That's the goal.
Right.
Challenge number 3 is automating compliance reporting. This seems like a universal pain point for almost any organization, probably magnified in a fast-moving DevOps environment.
Oh, absolutely. Organizations face this constant barrage of stringent internal requirements, maybe from the CIO, and then all the external regulatory stuff. GDPR, PCI DSS, HIAB-AA, SOC2, you name it. Meeting these demands requires generating tons of documentation, conducting audits, producing reports, and it's often incredibly time-consuming manual work.
And in a world where applications are updated daily, maybe even multiple times a day, manually gathering all that audit data across potentially dozens or hundreds of different pipelines, tools, cloud services, it must be incredibly complex and error-prone.
It's a significant hurdle, yeah.
Yeah.
Trying to integrate an automated audit trail that spans the entire interconnected SDLC from the initial commit through build, test, deployment, it's difficult.
So what's the solution there?
The most effective way to overcome this seems to be aggregating logs and activity data across all your CI/CD pipelines, your security tools, your deployment environments into some kind of centralized platform.
Bringing it all together.
Exactly. If you can bring all that disparate data together in a structured way, you can then build automated queries, dashboards, whatever, to search for specific builds, track security gates, verify compliance steps were actually executed, and generate the necessary audit and compliance files much more efficiently.
Turning a manual weeks-long process into something potentially done in minutes or hours.
Right. So centralizing that data stream from all those different tools is the key to unlocking automated compliance.
Makes sense. Okay, the fourth challenge is that the very tools you rely on for DevSecOps productivity often come with their own inherent complexities and risks.
Mm.
Modern DevOps environments rely heavily on this diverse ecosystem of open-source tools and dynamic cloud infrastructure. And while these are incredibly productive and enable speed, they also introduce new kinds of risks.
Like the potential for vulnerabilities within the tools themselves, or maybe lack of visibility into certain technologies like containers.
Both are definitely issues. Open-source tools can have vulnerabilities, absolutely. And dynamic environments like containers can obscure what's actually running unless you have the right visibility tools in place. But on top of that, there's the challenge of just tooling sprawl.
Too many tools.
Yeah, and a potential skills gap related to using them effectively. Different teams might adopt different, sometimes overlapping tool sets. There can be a lack of clear standards, maybe poor documentation or insufficient training,
Right.
making it genuinely hard for developers and ops engineers to effectively use the complex security tools integrated into their workflows.
Right.
This complexity also impacts consistency in configuration management and policy enforcement across the board.
So how do you manage the complexity of the tools that you need for security? It sounds a bit circular.
It can feel that way.
Yeah.
Developing clear tool standards and usage guidelines across the organization is crucial. You need to document the tools currently in use, their purpose, how they should be integrated, how they should be configured.
Get everyone on the same page.
Basically, yeah. This simplifies selection, usage, troubleshooting, and ensures consistency. Organizations also benefit from adopting platforms that can integrate with a variety of best-of-breed or open-source tools in a non-opinionated way. These platforms can sort of abstract away some of the underlying complexity, handle integrations, manage updates, provide a unified interface, helping to manage that tooling sprawl and reduce the burden on individual teams.
That leads us directly into challenge number 5, the skills shortage. We hear about a general IT skills gap everywhere, but it sounds particularly pronounced when it comes to DevSecOps and security skills within development teams specifically.
It absolutely is. The demand for professionals who understand both rapid development and security is just skyrocketing, and the supply isn't keeping up. The material we looked at cited some really eye-opening statistics.
Right.
Almost 40% of organizations struggle significantly to find DevSecOps professionals with sufficient security testing knowledge. And maybe even more concerning, that at least 70% of developers report that they lack adequate security training from their organizations to perform secure coding practices or even use the security tools provided effectively.
Wow, 70% lack adequate training. That's a massive gap. If developers aren't equipped with foundational security knowledge and tool proficiency, how can you realistically expect to shift left and empower them to fix security issues early?
You can't, not effectively anyway. This lack of developer security skills is honestly one of the primary inhibitors preventing organizations from truly realizing the full potential of DevSecOps.
So what's the answer? More training.
To overcome this, a strong, sustained focus on continuous education is just non-negotiable. A holistic training model that incorporates various approaches is necessary. Maybe in-house training tailored to your specific tools and workflows, leveraging third-party e-learning platforms, traditional classroom instruction for foundational concepts, structured on-the-job training, encouraging self-guided learning paths.
A mix of things.
Yeah, a broad approach. And for many organizations, especially those just starting their journey or facing significant immediate gaps, pooling expertise by bringing in third-party security consultants or managed services can help bridge those skill set gaps and rapidly bring internal teams up to speed through mentorship and practical collaboration.
Okay, challenge number 6 is managing false positives. This is a classic problem with security tools, right? But it seems like it could be especially overwhelming in a high-speed environment, just generating tons of automated alerts.
It is a very real and complex issue. False positives, those security alerts that are incorrectly flagged as potential problems but aren't actually vulnerabilities, they're a constant challenge. They often arrive in bulk, just flooding security and development teams with notifications. And without a clear, defined process for triaging and handling them, they can quickly overwhelm even large security teams, consuming significant time and resources.
And the danger isn't just wasted time, is it? It's the risk that real critical issues, the false negatives that the tools missed or that are buried in all that noise, get overlooked amidst the flood of false positives.
Exactly. They create significant alert fatigue and can cause teams to dismiss warnings or, worse, even disable the tools entirely because they're just too noisy.
So how do you tackle that?
Well, practical starting point is to prioritize addressing false positives for your most critical applications. First, the ones that directly impact customer experience or core business functions. Define and refine base rules and configurations for your security tools based on your specific application architecture and coding patterns to minimize the number of false positives they generate upfront.
Tune the tools.
Yeah, tune them. Using a multi-tool approach can also help sometimes. Different tools use different detection techniques, and while each might generate its own false positives, the overlap can sometimes highlight real issues more effectively. Conversely, a false negative from one tool might be caught by another.
Ah.
As teams gain experience with the tools and understand their specific outputs, they become much more effective at defining better rules, filtering alerts, and further reducing that false positive rate over time. It's an ongoing process.
And finally, challenge number 7, poor secrets management and access controls. This one sounds incredibly dangerous, especially in highly automated environments.
It is arguably one of the most critical and frequently exploited weaknesses in modern environments. Secrets, sensitive authentication data like credentials, API keys, SSH keys, database passwords, tokens. They're absolutely necessary for applications and automated processes to function.
Right.
But in that drive for DevOps speed and convenience, they're so often mishandled. Think about developers hard-coding credentials directly into code.
Still happens.
Oh yeah, storing them in plain text files, within repositories or container images, granting unnecessary root access to processes or users, or even just sharing admin credentials around.
Wow.
And automation and continuous deployment amplify the exposure risk dramatically if secrets aren't handled with the utmost care. A single leaked secret in a CI/CD pipeline could potentially grant an attacker access to your entire environment. It's that serious.
So how do you secure something that needs to be accessed all the time but must remain absolutely secret?
The fundamental principle is you have to remove sensitive data from your code, your config files, your accounts, standard development tools like version control, leverage dedicated secrets management solutions.
Like HashiCorp Vault or similar tools.
Exactly. These are centralized platforms specifically designed to securely store, manage, and distribute secrets. Applications or automated pipelines should only request the specific credentials they're allowed to use, right at runtime, and these solutions can automatically rotate or revoke those credentials after a set time or specific use. Additionally, robust privileged access management, or PAM, solutions are critical. PM helps monitor and strictly control access to highly privileged accounts and systems, and crucially, implement the principle of least privilege for everyone. Developers, testers, ops, even security teams should only have access to the specific systems and resources they absolutely need for their job, and no more. Minimize that blast radius.
That gives us a really solid overview of the key challenges in implementing DevSecOps effectively. But, even with the best practices and tools, breaches can still happen. What does incident response look like in this high-speed collaborative DevOps world? Is it different?
Well, incident response in a DevOps context maintains the core objectives of traditional IR, detect, respond, resolve, analyze, readiness, but it really requires a fundamentally different cultural approach and much faster execution.
Faster.
Yeah, and it mandates a culture of open, blameless communication between DevOps and security teams during a crisis. When an incident occurs, the focus has to be on resolving it quickly and learning from it, not assigning blame.
That blameless post-mortem idea.
Exactly. And developers are explicitly involved much earlier in the process compared to traditional models. Tasks are assigned based on expertise, not just predefined roles.
So developers aren't just brought in later if a code issue is suspected. They're part of the initial response team.
Precisely. They are critical resources for understanding the application's behavior, identifying code-related causes, and implementing fixes rapidly. The steps, while maybe similar in name, are executed with a DevOps mindset. First, detect. This involves proactive planning, comprehensive monitoring across applications and infrastructure, setting up detailed alerts, and having well-defined runbooks.
Runbook.
Yeah, pre-written step-by-step procedures for responding to specific types of incidents. Second, respond. This phase is about rapidly escalating the incident to the right people, often automatically based on alerts, and executing those runbooks to initiate containment and investigation. Third, resolve. This is where the cross-functional teams work together to contain the issue, maybe by rolling back a recent deployment or isolating affected systems, troubleshoot the root cause, and implement a fix, whether that's a code change, a config update, or a patch.
Okay.
Fourth, analyze. This is that critical post-mortem phase. It must be blameless, focusing on understanding what happened, why it happened, and how the systems, processes, and teams can be improved to prevent it from happening again. Lessons learned are shared widely. And finally, readiness. Based on the analysis, runbooks get updated, monitoring and alerting are refined, tools might be improved, training conducted to ensure the organization is better prepared for the next potential incident. It's a continuous improvement cycle.
Automation has been a constant theme running through this whole conversation. How is it specifically leveraged for security testing within DevOps beyond just running basic vulnerability scans?
Well, automation is really how you scale security testing to match the pace of delivery. We mentioned intervening static and dynamic analysis tools into the pipeline, right?
Yeah.
But it goes further. You can automate SaaS scans to trigger on every single code change, automatically opening tickets for developers to fix vulnerabilities, or even automatically halting the build entirely if critical flaws are found.
A hard stop.
Yeah. You can automate the application of security policies defined as code, like we discussed during the deployment process, to ensure compliance before an application goes live. You could automate DAS scans to run on newly deployed applications in a staging environment as part of the release pipeline. You can automate security tests that are triggered by specific events, like a new version of an application being deployed or a change in the underlying infrastructure. The goal is really to make security checks an automated, ideally non-blocking, part of the standard CI/CD flow.
And finally, how do you know if all these efforts, the shift left focus, the pipeline security, the incident response processes, are actually improving your security posture? How do you measure application security effectiveness in a way that's meaningful?
That's a great question. You absolutely need to define and consistently track security metrics and key performance indicators, or KPIs, right from the outset. These metrics provide tangible data points that allow you to understand your current security posture, measure performance over time, and evaluate the effectiveness of the security controls you've actually implemented. It shifts security from just a qualitative feeling, I think we're okay, to a quantifiable outcome.
What are some examples of these kinds of metrics that are particularly relevant in a DevSecOps context?
Good metrics usually focus on both preventative measures and response capability. So examples might include the number of attempted intrusions blocked, the number of actual security incidents that occur, and critically, metrics related to response speed.
Like how fast you react?
Exactly. Mean time to detect, MTTD. How quickly do you identify a security incident? Mean time to resolve, MTTR. How quickly do you fully remediate the issue? And mean time to contain, MTTC. How quickly do you stop the spread of an attack?
Those seem really key.
They are. Other important metrics include things like the mean age of open vulnerabilities in your applications. You want this number to be low and ideally decreasing. External security ratings or scores from third-party services can be useful benchmarks. And your patching cadence, how quickly are critical security patches actually being applied across your environments? Tracking these numbers gives you a much clearer picture of where you stand and where you need to improve.
Okay, we've covered the principles, the challenges, the processes. Now let's get really specific and look at how attackers are actively exploiting weaknesses in these very tools that organizations use for rapid delivery. The material describes a recent campaign called JINX-0132. What was that about?
Yeah, this campaign was notable because it specifically targeted publicly accessible web servers running common DevOps applications like HashiCorp Nomad, HashiCorp Consul, the Docker API, and Gitea. It really demonstrated that attackers are actively probing for and exploiting misconfigurations in these specific tools.
And the primary goal of the attack was cryptojacking, right? Using the victim's servers to mine cryptocurrency.
Yes, exactly. Cryptojacking is where malicious actors compromise a server or system and surreptitiously install cryptocurrency mining software. They then leverage the victim's computing power, CPU, GPU, electricity to mine cryptocurrency for their own profit, all without the victim even knowing.
Which hits the victim's bottom line through cloud bills or power consumption, degrades performance.
Absolutely. Degraded system performance, potential hardware damage. It's a real impact.
And this JINX-0132 campaign was particularly interesting because it was apparently the first publicly documented instance of misconfigurations in HashiCorp Nomad being exploited in the wild for this purpose.
That's correct. While cryptojacking itself isn't new and attacking things like exposed Docker APIs is a well-known tactic, this campaign highlighted that attackers are broadening their focus. They're now including other critical tools central to modern infrastructure automation and orchestration, like Nomad and Consul. It shows they're keeping pace with how organizations are building and deploying applications.
What was the attackers' methodology in this campaign? How did they operate once they found a vulnerable target?
A key characteristic observed in JINX-0132 was what security researchers call living off open source.
Living off open source.
Yeah. The attacker deliberately avoided using unique custom-built malware or relying on attacker-controlled infrastructure for delivering their payloads. Instead, they downloaded standard, publicly available tools like the XMRig cryptocurrency miner directly from legitimate public repositories like GitHub. They just used standard releases of these tools.
So they weren't distributing unique malicious files that security software could easily fingerprint or signature. They were using legit tools.
Precisely. This tactic makes detecting and clustering attacker activity based on traditional indicators of compromise, like known malware hashes or specific command and control server IPs, much, much more challenging. They blend in by using legitimate tools already available online.
Sneaky.
Very. The primary unique identifier researchers could reliably track was the specific cryptocurrency wallet address the attackers were mining to. And the value proposition for the attackers here was high. Compromised servers running orchestrators like Nomad often control significant pools of compute power across multiple nodes.
Oh, lots of horsepower.
Exactly. The material mentioned instances where Nomad was managing hundreds of client nodes, representing substantial aggregate CPU and RAM, that, if purchased as cloud resources, would cost tens of thousands of dollars per month. Exploiting relatively basic misconfigurations allowed the attacker to harness all this power for free.
Let's break down the specific applications they targeted and the exploits they used. Starting with HashiCorp Nomad, you said it's an orchestrator.
Yeah, HashiCorp Nomad is designed as a simple, flexible workload orchestrator. It's a scheduler that can deploy and manage applications across a cluster of machines. However, the material emphasizes a really critical point. It is not secure by default.
Not secure by default. That sounds bad.
It can be. Its core function involves accepting job submissions descriptions of tasks to run. By default, if the access controls aren't explicitly configured, any user who can reach the Nomad server's API can submit a job and have it executed on the cluster.
Which, if that API is exposed to the internet, is essentially granting anyone remote code execution. That's RCE.
Absolutely. It effectively gives unauthenticated attackers the ability to run arbitrary commands on the server and any connected client nodes. JINX-0132 exploited this exact default configuration.
How specifically?
The attacker would submit new jobs with random names, but using a specific, easily identifiable task group named nignog. The job definition would then instruct Nomad to download the XMRig miner binary directly from GitHub, give it full execution permissions using Chimba77.
Risky permissions.
Very. And run it, connecting to a public Monero mining pool, pool.supportxmr.com.443, and specifying their wallet address to receive the mined cryptocurrency.
So the exploit was a straightforward abuse of a default, insecure by default API configuration combined with Nomad's core job running functionality. What about HashiCorp Consul? That was targeted too.
Yes. Consul is primarily a service networking solution service discovery, configuration, segmentation. And similar to Nomad, its default configuration can be problematic. If it's configured to allow remote users registration access, those users can define new services and associate health checks with them.
Okay.
Critically, these health checks can be configured to execute commands on the nodes where the service runs. So if the default settings permit remote, unauthenticated access to register services and health checks, this also grants an attacker effective RCE capabilities.
Another RCE vector through default settings, and JINX-0132 used this one as well.
They did. In observed attacks, they added malicious health checks configured to download and run the XMRig miner. Logs from compromised instances showed successful mining activity originating from these exploited Consul health checks.
Wow. Okay, the Docker API is another tool mentioned. This one is a relatively well-known attack vector when misconfigured, isn't it?
It is, yeah. It's been exploited for years, but it's still a surprisingly common vulnerability. The Docker Engine API is the interface used to control the Docker daemon, build images, run containers, manage volumes, etc. By default, it's meant to be accessed locally via a Unix socket, which is secure. However, sometimes for convenience, troubleshooting, or integrating with remote tools, administrators will configure the Docker daemon to listen for connections over TCP, often on ports 2375 unencrypted or 2376 TLS encrypted, though attackers often try 2375 first.
And exposing that TCP port publicly is essentially handing someone the keys to the kingdom.
Absolutely. An exposed Docker API endpoint, especially without authentication, which was the default behavior on 2375 for a long time, gives anyone who can reach it the same root-level power as running commands with the root-owned Docker CLI directly on the host machine.
So they can do anything.
Pretty much. Attackers can trivially create new containers, including ones configured to mount the host file system, allowing them to access sensitive data, modify system files, launch privileged processes. They can also just launch container images with pre-built crypto miners or other malicious payloads. It remains a really high-risk misconfiguration.
And the final targeted application discussed is Gitea, the self-hosted Git service. How they get into that?
Gitea is a popular lightweight alternative to GitHub or GitLab that you run yourself. Initial access in these attacks was likely through either a vulnerability or a misconfiguration in the Gitea instance itself. The material highlights several potential vectors.
It says.
Well, older or misconfigured Gitea versions could be vulnerable to post-authentication RCE via Git hooks if the disable Git hooks setting isn't correctly configured or is manually enabled for users. So if an attacker gets user credentials somehow...
Think to run code?
Potentially, yeah.
Yeah.
There was also a specific, more critical unauthenticated RCE logic flaw in Gitea version 1.4.0. It allowed an attacker to forge an administrative session and then use the Git hook mechanism to execute arbitrary commands. That's obviously very dangerous.
Unauthenticated RC is bad news.
Always. Another simple misconfiguration risk is just leaving the Gitea installer unlocked after set up the install as TK false setting. If this flag isn't set to true, anyone can access the setup page and potentially reconfigure the instance, maybe change admin credentials or overwrite config files.
So a mix of leveraging known fixed vulnerabilities in older versions and exploiting insecure defaults or overlooked configuration settings across all these tools. What's the broader scale of the risk here? How common are these tools in cloud environments today?
The data is quite revealing and really underscores how prevalent these risks are. The material points out that approximately 25%, a quarter of cloud environments, utilize at least one of these technologies: Nomad, Consul, Docker, or Gitea.
Wow, 1 in 4.
Yeah, and Consul seems to be the most widely adopted, present in over 20% of cloud environments. Critically, though, of those environments using these tools, a concerning 5% expose them directly to the public internet.
Only 5% sounds small, but given the scale.
Exactly. And perhaps most alarming, among those deployments that are exposed, a significant 30%, almost a third, are found to be misconfigured in ways that make them vulnerable to the attack vectors, like those used by JINX-0132.
Let me make sure I'm following that math. A quarter of cloud environments use one of these tools. 1 in 20 of those expose one directly to the internet. And almost a third of those exposed instances are vulnerable due to misconfiguration. That still adds up to a non-trivial number of easily exploitable targets floating around out there.
It absolutely does. External internet scans consistently show thousands of exposed Nomad and Consul instances across the internet, with hundreds specifically located within major cloud providers like AWS, Azure, and GCP. This isn't some theoretical threat. It's a widely available target surface that's being actively probed and exploited right now.
That paints a pretty clear and frankly worrying picture of the threat. So given these specific attack methods and the prevalence of these tools, how can organizations actually defend themselves? What are the specific mitigations and best practices to fortify your environment against attacks like JINX-0132 and similar threats?
Okay, yeah, let's talk defense. For the specific tools targeted by JINX-0132, there are direct, impactful mitigations. For HashiCorp Nomad, the most critical step is implementing access control lists, ACLs. Yeah, ACLs are a security mechanism within Nomad that allows you to define detailed rules about who or what is allowed to access specific resources or perform actions, like submitting a job. Implementing ACLs to deny unauthenticated access to sensitive features like job submission is absolutely essential. You have to move away from that insecure default. Organizations must follow and tailor the vendor's security recommendations rigorously.
Makes sense. Secure the API. What about HashiCorp Consul?
Similar story. Using ACLs is fundamental to restrict access. Additionally, you should disable script checks by setting Enable Script Checks false in the console configuration. That prevents health checks from executing arbitrary commands on your nodes, which was that key exploit vector we talked about.
Right.
And wherever possible, restrict the console HTTP API to bind only to local host or specific internal network interfaces. Prevent remote public internet access entirely if you can.
The defense for the Docker API seems pretty straightforward, yet, as you said, often overlooked.
It is. The simplest and most effective defense for the Docker API is just fundamental. Do not expose it to the public internet. Period. The Docker daemon API is designed as an internal interface for managing your local container runtime. Publicly exposing it, especially unauthenticated, is just an open invitation for attackers to take control of your host machine.
Use SSH tunnels or something if you need remote access.
Yeah, use SSH tunnels or other secure methods for remote access if absolutely necessary, but avoid direct public TCP exposure at all costs.
And for Gitea instances, what are the key defenses there?
Pretty much basic security hygiene and configuration. Keep your Gitea instances updated to the latest versions. That ensures you've patched known RCE vulnerabilities like that nasty one in version 1.4.0. Be extremely cautious about enabling Git hooks and ensure the disable Git hook setting is configured appropriately, preferably defaulting to true. And definitely don't leave the installer unlocked, install it false. Always set this flag to true after the initial setup to prevent unauthorized reconfiguration. If you absolutely need Git hooks, implement strict access controls and validation on what commands can even be executed through them.
Okay, those are good specific tool mitigations. But stepping back, securing your broader container environment, particularly when using Docker, requires a more comprehensive, layered approach, right? It starts with the foundation.
Exactly. It starts with the very foundation, securing the host OS that runs your Docker daemon and containers.
Why is the host OS so critical to container security? I thought containers were supposed to provide isolation.
Well, they provide a degree of isolation, yes, but they share the host OS kernel. That's the key. If an attacker compromises the host operating system, they can potentially break out of the container and gain full control of the underlying machine and everything running on it.
Ah, okay. Host compromise is game over.
Pretty much. Therefore, the security of the host OS is paramount. A best practice is to use a container-specific host OS. These distributions, think like BottleRocket from AWS or Fedora CoreOS, are typically built with a minimal attack surface, include built-in security features, automated updates, and hardened configurations, specifically designed for running containers securely.
As opposed to a general-purpose OS?
Right. Using a general-purpose OS means you have a much larger attack surface to manage, potentially unnecessary services running, and it requires diligent manual effort to configure, patch, scan, and monitor for vulnerabilities consistently. A purpose-built OS gives you a more secure and easier-to-manage foundation.
So, nail the host OS security. What about securing the Docker images themselves? This seems like where a lot of potential vulnerabilities could be introduced during the build process.
Securing your Docker images is absolutely vital because vulnerabilities baked into an image propagate to every single container spun up from it. So first things first, always use official, trusted Docker images as your base image, the from instruction in your Docker file.
Official images from Docker Hub or vendor registries.
Yeah. These images are maintained by vendors or the Docker community and are generally built with better security practices than trying to start from some generic OS image and installing everything yourself. And try to use official application images like node.ltsdes-alpine or Python-bot 3.9 slim rather than building your application on top of a full OS distribution like Ubuntu or CentOS if you can avoid it.
And choosing small-size images within those official options is important, you said, for attack surface reduction.
Crucially important. Opt for lean distributions like Alpine Linux or, even better where possible, Google's distroless images. Full OS distributions come packed with binaries, libraries, package managers that your application likely doesn't need at runtime. This significantly increases the image size, sure, but more importantly, it increases the attack surface.
Fewer things for an attacker to use.
Exactly. Smaller images mean less storage, faster transfer, but their primary security benefit is that minimized attack surface. With fewer libraries and tools included, there are significantly fewer known CVEs present and fewer places for an attacker to hide malicious code or leverage those living off the land techniques. Distroless images take this to an extreme. They contain only your application and its direct runtime dependencies, nothing else, dramatically reducing the potential attack surface.
Multi-stage builds also help with image size and attack surface, right? Can you explain how they work?
They do, yeah. Multi-stage builds allow you to define multiple from statements in a single Docker file. You can use an initial stage, let's call it the builder stage, with all the compilers, build tools, SDKs, and dependencies needed to compile or build your application. Then in a second stage, you start from a much leaner base image, like that distroless image, and use a copy Y from builder.instruction to copy only the necessary application artifacts, like the compiled binary or script, from the builder stage into this final lean runtime image.
So none of the build tools end up in the final image.
Exactly. This separation ensures that none of the build time tools or dependencies that are not needed at runtime end up in your final deployed image, further reducing its size and, again, that critical attack surface.
What about file permissions within the image? Is that something to watch?
Definitely. A key security best practice is ensuring executables and critical scripts within the image are owned by the root user and are not world writable.
Even if you run the container as non-root.
Yes, even if you configure your container to run as a non-root user, which is also a very important best practice. Ensuring the binaries themselves can't be modified by that non-root user helps maintain the integrity and immutability of the container. The non-root user only needs execute permissions, not write permissions, on the binaries they need to run.
Using a Docker ignore file seems like a simple but effective step, too.
Absolutely. Creating a Docker ignore file in the root of your project directory is essential. It works just like .gitignore. You list files and directories that Docker should exclude when it's building the image context.
Ah, so it doesn't even send them to the Docker daemon.
Right. This prevents accidentally including unnecessary or sensitive files, things like auto-generated build folders, node modules, target, temporary files, log files, or even worse, private keys or configuration files containing secrets that should never ever be in the image. It helps keep your image clean and reduces its size and potential exposure.
And avoiding the latest tag on base images in production is a classic piece of advice, but probably important to reiterate for security reasons.
Absolutely critical. Never use the .latest tag in production Docker files. Just don't. The image that .latest points to can change at any time without warning, introducing unpredictability into your builds. You might inadvertently pull in a new version of the base image with unexpected changes, breaking your application, or worse, introducing new, unreviewed vulnerabilities.
So always use specific version tags.
Always use specific fixated image versions. For example, Python 3.9.18 Slim Bookworm or Node.2-Alpine 3.19. The more specific the tag, the better. This makes your build process predictable and transparent, ensuring you know exactly what's going into your image every single time.
What are some other key best practices for building secure Docker images?
Okay, a few more important ones. Include a health check instruction in your Docker file. This tells the Docker daemon or your orchestration platform, like Kubernetes, how to check if the containerized application inside is actually running correctly and responding. Docker or the orchestrator can then use this information to manage the container's lifecycle, maybe restarting it if it becomes unhealthy.
Okay, smart.
Optimize image layer caching. Docker builds images layer by layer, right? Each command like runn, copy-y, add potentially creates a new layer, and these layers are cached. To speed up builds, you want to maximize cache hits. So structure your Dockerfile commands carefully. Order them from least frequently changing to most frequently changing.
Example.
Sure. Things like installing base packages or dependencies, run apt-get update and apt-get install or copy-y requirements.txt, followed by run pip install, should come before you copy-y your application source code, which probably changes much more often. This way, if only your source code changes, Docker can reuse the cached layers for all the dependencies, making builds much faster. And critically, we touched on this as a major challenge. Avoid storing secrets directly in Docker images. Passwords, API keys, certificates. These should never be baked into images in plain text or even lightly obfuscated forms. Image layers can be inspected, and extracting secrets is often trivial. Don't put them directly in Docker file instructions, especially env or arg commands that might leave them visible in the image history.
So how do you handle secrets then?
You inject them at runtime. Use environment variables, but use them cautiously as they are visible to processes running inside the container. Use Docker's built-in secrets management features, like in Docker Swarm or Kubernetes Secrets. Use build time arguments, build arg, only for injecting sensitive build time configurations that don't end up in the final image layers, or use encrypted shared volumes mounted into the container at runtime. Keep secrets out of the image itself.
Preferring copy-y over ADD is another granular tip that helps with predictability you mentioned.
Yeah, it's a subtle but good practice. Both copy-y and ADD copy files into the image. But ADD has some extra magic features, like being able to download files directly from URLs, or automatically extract compressed archives like tarballs or zips. Copy-y is simpler, more predictable, and generally less prone to unexpected behavior or potential security risks related to fetching remote content or auto-extracting potentially malicious archives. Use ADD only if you specifically need those extra features. Otherwise, just stick with the simpler, safer copy-y.
What about user ID binding?
Be mindful of user ID, UID binding, especially on platforms like OpenShift that often run containers with arbitrary random UIDs for security reasons. If you hardcode a specific non-root UID in your Docker file, like USR 1001, it can sometimes cause permission issues, particularly with mounted volumes that expect specific ownership, or it might break the service entirely on those platforms. It's something to be aware of depending on your deployment environment.
And finally, image security needs to be a continuous process, right? Not just a one-time check during the build.
Absolutely. Security is never static. You need to automate the building and, critically, the security testing of your images as part of your CI/CD pipeline. Set up tooling for continuous image analysis and vulnerability scanning that runs automatically after images are built and pushed to your container registry.
Scan them regularly.
Yes, and crucially, establish processes to automatically rebuild your images when new vulnerabilities are found in your base images or dependencies, or when those base images are updated by the vendor with security patches. Stay current. And use consistent documented static image tags in production. Follow a clear policy like semantic versioning, app.12.3, or maybe use the git commit SHA, app.abcdf01. This provides clear links between image versions, software releases, and the code used to build them. Clarity is key.
Okay, so that covers securing the host OS and building secure images pretty thoroughly. What about securing the Docker container runtime itself, the container once it's actually up and running?
Right. Securing the container runtime involves applying security controls and configurations when you actually launch a container using Docker Run or via your orchestrator. Key best practices here include: never ever run containers in privileged mode, unless you have an extremely specific, well-understood, and unavoidable reason. Privileged mode essentially disables container isolation and gives the container full capabilities of the host. It's incredibly dangerous. Got it. Avoid privileged. What else?
Avoid exposing unused ports on your containers.
Yeah.
Only expose the specific ports your application actually needs to function. DAF flag. Don't share the host's network namespace, nethost, unless absolutely required, as this bypasses container networking isolation. Use isolated container networks instead for better segmentation. Add resource limits, CPU limits, C+ memory, to your containers to prevent denial of service scenarios where one compromised or misbehaving container could potentially consume all host resources and starve other containers or the host itself.
Resource limits are important.
Very. Set an on-failure restart policy. Restart on failure, so Docker can automatically attempt to restart a container if it crashes or exits unexpectedly. Where possible, set container file systems and volumes to read-only. You can mount specific temporary directories as writable if needed, TMSE for MVP. Making the root file system read-only prevents attackers or buggy applications from writing unauthorized files within the container, making it much harder for them to install malware or modify critical files, reinforcing immutability. And running Docker itself as non-root.
Yes, consider running the Docker daemon itself in rootless mode. This runs the daemon in containers as a non-root user on the host, significantly limiting the potential impact if the daemon itself were ever compromised. It adds another strong layer of defense.
Wow, that's a significant number of individual best practices across the host, the image build process, and the runtime. For organizations managing complex hybrid or multi-cloud environments, trying to implement and monitor all of this consistently across potentially thousands of workloads sounds incredibly challenging. Is there a way to unify visibility and protection across all that?
Yes, absolutely. This is precisely where modern solutions designed specifically for the complexity of cloud and hybrid environments come into play, particularly cloud workload protection platforms, or CWPPs.
CWPPs. Okay, what are they exactly?
A CWPP is essentially a workload-centric security tool. It's designed to provide visibility, monitoring, and protection for diverse types of workloads: physical servers, virtual machines, containers, even serverless functions, regardless of where they happen to be running. On-prem, in AWS, Azure, GCP, wherever.
So, unified protection across different environments. What capabilities do they typically offer to achieve that?
They generally provide a centralized platform for unified visibility into all your workloads across these different environments, and they offer multiple layers of protection. CWPPs typically include scanning capabilities for vulnerabilities, misconfigurations, and malware within your workloads, and sometimes their underlying infrastructure or configuration. They provide real-time threat detection using techniques like machine learning, behavioral analysis, and checking against known indicators of compromise to spot malicious activity as it's happening.
Real-time detection.
Yeah. They can often automate responses to detected threats, like automatically isolating a compromised workload from the network or triggering an alert in an incident response system like PagerDuty or Slack. And they allow you to centrally define and enforce security policies like required configurations or allowed network connections across your entire workload fleet, regardless of location. The material actually details several key control layers typically integrated into a comprehensive CWPP. There's hardening, configuration, and vulnerability management that's continuously scanning workloads, comparing configurations to secure benchmarks like CIS, and helping prioritize vulnerability remediation based on risk.
Okay.
Then there's network firewalling, visibility, and microsegmentation. This allows you to define and enforce network segmentation policies between workloads controlling that east-west traffic, limiting communication paths only to what's necessary, and monitoring network activity for suspicious patterns, which helps prevent attackers from moving laterally if they manage to compromise one workload.
Limiting the blast radius again.
Exactly. System integrity assurance monitors critical system files and processes, both pre-boot and post-boot, to detect unauthorized modifications or things like rootkits. Application control and allow listing enforce a default deny posture, meaning only explicitly approved applications and executables are allowed to run on a workload, effectively blocking unknown or malicious binaries.
Default deny sounds powerful.
It is. Exploitation prevention layers use techniques to prevent common exploit techniques like buffer overflows or ROP attacks from succeeding, even if an underlying vulnerability exists. And crucial for countering threats like the cryptojacking we discussed, there's runtime protection and behavioral monitoring. This constantly observes workload activity, CPU usage spikes, unusual network connections, unexpected process execution, weird file access patterns using behavioral analysis to detect anomalies indicative of threats like cryptocurrency miners, ransomware activity, or unauthorized data exfiltration. They also often incorporate server workload (EDR), endpoint detection and response capabilities, general threat detection, and anti-malware scanning specifically tailored for server workloads.
It sounds like a CWPP provides a really comprehensive layered defense specifically for the workloads themselves, kind of bridging the gap between the cloud provider's infrastructure security and the application security measures.
That's exactly right. CWPPs are designed to support that shared responsibility model in the cloud. They pick up where the cloud provider's security of the underlying infrastructure ends and provide deep protection of the operating systems, applications, and containers running on top of that infrastructure.
And the benefits, unified view.
Yeah, they offer that critical unified visibility across complex hybrid and multi-cloud environments where trying to manage a patchwork of disparate point tools becomes untenable. This enables more proactive threat mitigation with real-time detection and potentially automated responses. It can lead to significant cost efficiencies compared to managing numerous separate security tools. And it helps ensure a consistent security posture, which is really important for compliance assurance.
How should an organization approach implementing a CWPP effectively? Any tips there?
Well, you should design your implementation with continuous visibility and control as the primary goals. Adopt zero-trust principles, assume no workload is inherently trusted, implement strict controls like default deny application policies, and runtime monitoring. Integrate the CWPP's capabilities directly into your DevSecOps pipelines.
Shift left again.
Exactly.
Oh.
Allow developers to get security feedback on their images and configurations early in the cycle from the CWPP scanner. Leverage the platform's API-driven functionality extensively to automate security tasks, policy enforcement, and incident response workflows. And make sure the platform supports agentless deployment scenarios where needed for environments where installing agents isn't feasible or desirable, although agent-based usually provides deeper visibility. And looking ahead, the security landscape is definitely seeing convergence in the cloud space. CWPP capabilities are increasingly integrating with other crucial cloud security domains. Things like Cloud Security Posture Management, CSPM. CSPM focuses on continuously auditing and enforcing secure configurations of the cloud infrastructure services themselves. Things like S3 buckets, security groups, IAM roles, and also Cloud Infrastructure Entitlement Management, CIM, which focuses specifically on managing permissions and access rights within the cloud environment to enforce least privilege across users and services.
And this convergence is leading to what's being called CNAPP.
Yes, Cloud Native Application Protection Platforms. CNAPPs are emerging as these unified platforms aiming to simplify the complex cloud security stack by providing end-to-end protection across the entire cloud native application lifecycle, right from development through to production. CWPP, with its deep focus on workload protection, is really a foundational cornerstone of that CNAPP model. It provides the essential runtime security, vulnerability management, and threat detection for the applications and services themselves within that broader security framework.
Okay, let's try and pull all these threads together then. What's the main takeaway from our deep dive today into securing these rapid DevOps environments?
I think the key insight is that achieving both speed and security in modern, rapid development environments isn't a zero-sum game, but it's also definitely not about finding one magical tool or process. It really requires a holistic, integrated strategy. This means actively integrating security practices throughout the entire SDLC, really embracing that shift-left mentality, and empowering developers and operations teams with the tools and knowledge. It involves specifically securing the foundational tools that are central to your high-speed operations, the DevOps platforms, the CI/CD pipelines, the container runtimes, because, as we saw, these are becoming prime targets for attackers.
Right. And it demands implementing strong foundational security practices at every single layer, from the host OS all the way up through building and running secure container images.
Exactly. And then leveraging modern, comprehensive platforms like CWPPs to provide that essential unified visibility and protection across increasingly complex and distributed hybrid and multi-cloud environments.
Yeah.
And while advanced tools are necessary, it's just crucial to remember that attackers are often succeeding by exploiting really fundamental issues. Basic misconfigurations, default settings that are insecure by design, and known unpatched vulnerabilities in widely used software. Good security hygiene, diligent patching, secure configuration management. They remain incredibly important alongside any advanced detection and protection tools you deploy. Don't forget the basics.
So achieving both the speed and agility promised by DevOps and robust security is possible, but it requires a deliberate, multifaceted, and continuously evolving strategy that truly builds security in from the ground up.
Absolutely. It's all about making security a continuous, integrated part of the process, rather than seeing it as an afterthought or an obstacle to overcome. It has to be part of the flow.
Okay. We've taken a pretty deep dive into the challenges of securing rapid software delivery environments. We looked at specific real-world attacks targeting common DevOps tools like Nomad, Consul, Docker, and Gitea, and we've explored a layered defense strategy, from secure coding and container image best practices all the way up to comprehensive platforms like cloud workload protection platforms.
It's definitely a complex and constantly shifting landscape, isn't it?
Yeah.
New threats are always emerging as the technology itself evolves.
Which leaves us with, I think, a compelling question for you, the listener, to consider as you reflect on this deep dive. Given the constant evolution of attack methods and just the sheer velocity of modern software development, how can organizations not only ensure their security practices keep pace with current threats, but actually proactively anticipate and build resilience against the next wave of attack vectors before they even materialize? It's a huge challenge that demands continuous learning, adaptation, and maybe a fundamental rethinking of how security is integrated into everything we build and run.
Food for thought.
Indeed. And finally, this deep dive was made possible by Stonefly. They provide secure, ransomware-proof enterprise storage solutions, including air-gapped and immutable storage designed specifically to protect your critical data against modern threats like ransomware.
Very important stuff.
Absolutely. To learn more about how Stonefly can provide a secure foundation for your data infrastructure, just contact sales@stonefly.com to schedule a demo.